Okay. So today is the 25th of June, and we do not have a homework assignment due for today, but we will on Thursday. And it'll be pretty substantial, so then, whatever work you might be able to have gotten done already would be great, but yeah, so we're going to go through all of this stuff today. And then hopefully, I'm not sure, but possibly I might have your exams graded by Thursday. And then we'll go from there. I want to give some context, right, to all that we're doing. Some idea of what's actually happening here with these things. And so we'll kind of back up a little bit and we'll deal with the purpose of statistics first. Okay, so what are we talking about here? Purpose of statistics. Okay, data-driven decisions. What does that mean?
What to expect.
Okay, and what does that mean?
Below 5%. It's unusual.
So below 5% would be considered unusual. And what else?
Above 95%. Expected. Yes.
Like a yes. Okay. So, sure. Well, it makes sense to close. Around. All right, so specifically then, what do we want from the process of statistics?
Use the sample to understand the population.
Okay, we're going to use the sample to understand the population. So what role does the confidence interval play in this process? What is the purpose of the confidence interval?
Describes the measure of the population.
Okay, confidence interval is going to describe a measure of the population. And it's going to be using a sample in order to do that. So when we say, okay, what do I want to know? The answer is I want to know some kind of a measurement about the population. And then when we say, how are we going to know that? We're going to use a sample to understand that, but we are not going to get a single number answer. Single number answers are not good because remember when we talk about what to expect, there's no way that we can have 100% sure about any number that we have in statistics. The numbers are always changing. So that when we say, for example, I think the unemployment in La Crosse next month is going to be 4%. That would be a bad statement to make because it's impossible for you to be exactly right. Because it's impossible for you to have exactly 4%. You would possibly want to say, I think the unemployment in lacrosse next month will be between 3 and 5%. That makes a lot more sense because then you could actually be right about what you're saying. If you say it's going to be 4% and it's not, then you're wrong, quote unquote. So then when we say, how do I know how to actually make this work? How do I know how to actually say what I expect to happen? We're not going to say single numbers. We're going to use intervals, and we're going to use the confidence interval. Now, most people, when they see a confidence interval, they don't understand what it's actually measuring. The confidence interval is measuring something about the population. And so then when we look at a confidence interval, we say, I believe the population number is between these two numbers. We don't really care about the actual sample number. We really care about where the population number is, and it's somewhere between these two numbers. Now with the confidence interval then, we also are going to control the sample variation so that we know that samples are always different, but because we're using an interval, then we can say, I know this within a certain range of things. I know how much variation, how much change might happen in this thing based on what I have. Now, this is not a perfect system. There's a lot of mathematical things behind the scenes here that we're not talking about. And so we're using it, but we're just kind of like, well, we think this is going to work pretty well. And generally it does. So when we look at this and we say, okay, what's important for me to be able to do the confidence interval? Then we need to have a formula that we're going to use for that. Now, in your in Blackboard, there is a list of important formulas and tables. And this one right here is the confidence interval for the proportion. This is what you wrote down last time when we went through this. This is what the equation looks like. So now we need to find out what all these numbers are. How do I find p hat? Can someone tell me what to do to find p hat?
X divided by n.
X divided by n, what does that mean, Sierra? Okay. I want somebody to tell me what it means. Yes, Abby.
Is it the percentage of the total?
Yes, percentage of what?
Of X over the total?
Okay, what does X mean? What does it mean in the single house?
It's a variable, like, it depends on what you're trying to find.
Kinda, sure. All right, let's say I'm interested in side effects for people who take ibuprofen. What would X represent?
People that have side effects over the people having the whole.
Okay, yes, the number of people who have the side effects over the whole group. So X is the number of people in a specific category out of the total number of people that I asked. This is also known as the relative frequency. It's the relative frequency, and it's also the observed probability. And it's, okay, I'm going to write these down. This is relative frequency. This is the observed probability. And this is the sample proportion. Those are all things that are true. Okay. What is Q hat?
1 minus p hat.
1 minus p hat. N, we've already talked about, is the total number of people that were surveyed. Now, I just want you to be really careful about what you're doing right now. If you're writing this down, that's good. If you're writing down what Q hat is, that's not so good. You should have already written that down. Okay, that should already be in your notes. What you got there. Okay. Then we have this question. What is Z of alpha over 2? How do we determine what that is? There are 3 of them that we normally use. And I want to know what those numbers are and what they correspond to. I have 3 different numbers based on 3 different things. I want to know what those numbers are and where they come from. Okay, so Sierra's done answering questions now. Somebody else tell me what symbol that is for those 3 things. I'm sorry? Alpha. This is alpha. Crystal, can you tell me what alpha actually means?
The chance of being wrong.
It's the chance of being wrong, yes. Alpha is the chance of being wrong. And I want it to be small, and I normally, in most situations, I choose it to be 0.05. There's something that happens in the rest of the course, and that is if I don't tell you what alpha is, you assume it's 0.05. Generally, all the way through, every day that we go through from here on out, somebody will ask me, is it 0.5 because you didn't say so? And I will say, yes, it's 0.5 because I didn't say so. In the homework and on the test, it'll be clearly written, use alpha equals this. When we're in class, generally, we're going to start with always taking alpha to be 0.05. Okay. So what numbers now correspond to those things?
Are you talking about the confidence level or the Z-score that goes with it?
That's a great question. Let's go with both. I was thinking just Z-score, but we should have confidence levels. So what do you got for me, Emily, for confidence levels?
For the first one, it'd be 99%, 95%, and then 98%.
Okay. So when you think about the fact I have a 1% chance of being wrong, I am 99% confident in my results. Okay? Now somebody other than Emily tell me what are the Z-scores that correspond to those?
2.58, 1.96, and 1.64.
2.58,
58
1.96,
and 1.64.
1.64. Now,
Or 1.65.
I think I said that in the homework they use 1.65. So we'll go ahead and put that as a 5. Yeah. So what's happening here is that we are able, in this formula, to adjust the size of the interval based on how much confidence we want to have in the result. So let's do one of these. Let's say I ask $250 people. Do you watch hockey on TV? And let's say I had 30 people said yes. That would be one possible way the problem could be stated. Can somebody tell me what is P hat in this situation?
Point 12.
So I could have said 12% said yes. Okay. Now, as it turns out, if we want to do this, it is important that we would have a nice bell-shaped thing going on. If I have 250 people and I have 0.12, then we're okay. So it is nicely bell-shaped here. All right. So what I want right now is I want you to find the 95% confidence interval for that portion. I'll give you a couple minutes, see if you can make this work. So what's going to happen right now is I'm going to turn the screen off because I assume you've written down this formula. All right, so check with your neighbor, see if your neighbor can give you good information about this.
So what this calculator, you don't have to do the extra step, like you can just put the whole thing in, and then the parentheses, and it does the whole thing. Yeah, I bet you have, so Tia can put in her calculator, it's like Tia, you have to fancy your calculator, you don't have to do as many steps with it. So, yeah, I got that.
Okay.
That's 196.
All right, so we'll put the formula up here. And see if we can get this to work.
When we write our final answer, can we put a dash, or do we actually need to do like the .AP, that number, like for a final answer?
Okay, technically, for your final answer, you can use words. And you can say between numbers and
Number, okay.
that would be okay. This is some kind of switch here. There we go.
0.0797.
All right. So, Liz Tomitz, can you tell me what P or what Q hat is?
0.88.
Okay. So I've got 0.12 here. Liz, can you tell me what my Z-score is going to be for this?
1.96.
Okay, minus 1.96. And then here I have 0.12 times 0.88. And what's on the bottom of that fraction, Liz? 250. Now, when we ask the question, how much rounding off should you have on this? It's generally reasonable to round off to 3 decimal places here. Because when we're talking about percentages, most people only would go to that far of an accuracy here. Liz, you got an answer for me?
The final answer?
Yeah.
8% to 16%.
8% to 16%. All right. So if you did not get those numbers, then we need to fix that problem, right? Question. This is a 95% confidence interval. That means our confidence level is 95%. So the Z-score we use for that is 1.9. Now, it is possible, if you want, to go onto your E table and find out the area of the two tails based on alpha divided by 2, but you don't have to do that because these are the only things you have to know. So this is all you have to do. All right, so other questions about this process and making this thing happen right here? Once again, it's possible for me to go down the line and ask each individual, did you get this answer or did you not? But I'm going to allow you the luxury of being an adult so that if you have a problem, you let me know. Question, Kristen.
Are we gonna be given the Z-scores, like this like little table on the
Yes.
test?
I have.
So when you're plugging these scores into the formula, you just completely ignore the alpha divided by 2.
Okay, the alpha divided by 2. Can someone tell me what is the alpha divided by 2? What does it actually mean?
A label.
It's a label on the z telling me which one it is. So it's not actually a number that's put into the formula. In this case, since alpha is equal to 0.05, alpha divided by 2 would be 0.025. And if we wanted to, we could use that to get this number. But it doesn't actually appear in the formula. It's just a label telling me which one of these to pick.
Yeah, that's a good one.
Okay.
I multiplied the z-squared times 0.
Right, but that's not what it is.
Yeah.
It's a label. It's not an active number in the formula. Right.
Can you explain the whole process and kind of like a systematic, like step by step?
Sure. P hat is 0.12. I'm putting the numbers into this formula. So I know P hat is 0.12. I know it's a 95% confidence interval. And so I'm going to, when I look at this, I'm going to pick the 1.96. I know my P hat is 0.12. Q hat then is 1 minus that. So that's 0.88. So I'm just putting numbers into the formula. I just start from here and I just go through the formula. So this is 0.12, this is 1.96, this is 0.12, this is 0.88. Then when I ask the question, what's n? It's the number of people that I asked. So I put that in here. Probably the best option for this problem right here is that I would put this whole thing with the square root into my calculator and find out what that is. Then I would take that number times 1.96. That part needs to be separate. Okay? So then I have 0.12 minus that number, and that tells me this one is up. And then in the formula, I also have 0.12 plus that same number. And so then that goes in there. Great question. Thank you. All right. So then, the next thing that we want to consider is that we have this thing which we added and subtracted. We can write this formula this way: P hat minus capital E, P hat plus capital E. This thing, capital E, is called the margin of error. Now, this is really important to us because this is where we are controlling the variation. We're saying, how wide is my interval? How accurate do I need this thing to be? And so when I look at that, I see that in this formula, I have an n on the bottom of that part of the formula. So what this means is large N creates small error, or E. This is almost like the, I don't know what you would call it, but it's like the practical application of statistics is this right here. If I'm going to say, what do I need in practical terms in order to do statistics, I have to be able to deal with this thing right here. That I need a large enough sample in order to have a small amount of error. Because if my error is way big, then I can't say very much. So I want to try to be able to have good results. Like we were saying, if somebody says, I can take you out to lunch, it'll be somewhere between $0 and $100. Correct as that is, it's just not very helpful. I want helpful results. So I want then to have a small interval if possible, and I can get that by using large sample sizes. You need to be careful though. Some statistics people get all caught up in this and they think this will make everything beautiful. And the answer is no, it won't. Even though you have 10,000 people in your survey and you have like side effects, you're measuring side effects, you got 10,000 people. Just because you found a certain thing does not necessarily mean it's going to be true for 1 million people. You just don't know the answer to that question. So just because you have a really large sample and you think you have good results does not mean it actually is going to work, because these things are always changing. So you don't necessarily know what's happening. Okay. So then, what we're able to do, this is our next formula that we're going to use. And so what we're going to do is find the sample size for specific capital P. So the way this would normally be stated would be something like within 3%. That would be P. I want to try to be accurate. So when I look at this and I say, all right, if I want to know how many people actually watch hockey, and I actually want to know it within 3%, then I've got a formula I can use to make this happen. So this also is on the list of formulas, but I'll just write it up here so you don't have to go back and forth. N is equal to P hat, Q hat, multiplied by something in parentheses, which will be squared, and that is Z of alpha over 2 divided by E. But the big problem that people have with this is that E is actually a decimal. So you have to take that number E and make it into a decimal. You do not put the number 3 when it says 3%. What do you put in?
0.03.
0.03. So now we're going to make this happen. N is equal to 0.12 times 0.88. And we have to be told the confidence level that we're interested in. So we're going to say 95% confidence interval. So that'll be 1.96 divided by 0.03. We square it. What's the big deal here? The big deal is that you recognize the numbers from the statement of the problem and you put them in the right place. P hat is something which came from a previous survey which had some kind of accuracy. Q hat is 1 minus P hat. The Z based on the confidence. And then E is given to you in the problem. I want it now to be 3% for the plus or the minus. So, Mattia, do you got a number for me? Not yet? Okay. Lena Schmidt, do you have a number for me?
I have 450.7.
450.7. So if we're saying how many people are we going to ask, we'd probably say 451. Neat. Well, how big of a deal is this? How many people would you have to call on the phone in order to get 450 responses? Any ideas? You're calling people on the phone. How many of them are actually going to answer the phone and take the survey? Would you say maybe a tenth? So you'd have to call 5,000 people in order to get this to happen. How many people can you call in, let's say, an hour? $50 maybe? So you'd have to do that for 100 hours. Let's say you're making $10 an hour. That's $1,000. It's going to take you $1,000 to do one survey in order to get this accuracy of 3%. What if you want more accuracy? Oh, your numbers are going to get huge. Most of the surveys you see out there done by news organizations are approximately this accurate. They usually get somewhere around 400 maybe. And sometimes what they'll do is they'll do it over a period of days. So they'll say within the past 3 days, we got 400 people. Well, maybe then you say, well, how about the past week? We'll just add all those numbers together. Maybe it'll work. Maybe it won't. But let me show you how this works in an actual practical example then. So you might be aware that there's a presidential election coming up pretty soon. And here we got Bernie in Wisconsin for the Democratic primary. 39% of the people, Democrats that they talk to, like Bernie. Joe Biden, 24%. Turns out that you guys, 18 to 30-year-olds, actually give Bernie 61%. So Bernie's a lot more popular among your demographic compared to anybody else. Over 65, Biden is actually the one who leads. Turns out there are a lot of older people who vote, not as many younger people. So then it makes a difference what the older people think because they're the ones who actually vote. So that's a problem because sometimes younger people have to like work at a job. And so then they don't have time to just go vote whenever they feel like it. So just in case you're wondering, you should vote. And maybe you should like do an early ballot or something like that just to make sure you get it done. Don't just wait until the day and then, oh, I have to work or something. Anyway, that's just for you younger people. Not that I'm a Bernie guy or anything like that, but just for you to be able to vote is really important, so you got to do it. But notice, n is equal to 324 plus or minus 5.4%. This is their margin of error. 324 people, 5.4% is their margin of error. So when you look at these numbers, is Bernie at 39? No, he's not. Where is Bernie? Where is his support? What is the actual percent? It could be anywhere from 34 to 44. The same is true for all these numbers. There's plus or minus on them. But you can't see it because they just put it on the graph, okay? They don't put the margin of error on the graph. They should, because these numbers are not true. This is not what's actually happening. These are the sample numbers, which we know are incorrect. The population numbers will be somewhere in an interval, but they don't put that on here because they want people to think they know what's going on when they actually don't. They don't know what's going on. Within those 5%, they could say certainly Bernie is ahead, but they don't want to have to mess with the margin of error stuff. But they should. Anyway, so that's margin of error, and that's part of what you need to be able to do on here. So, yeah, I think, okay, I'm just going to try for the next 10 minutes. I'm going to try to get us into the next topic. All right. What happens next? Well, what we had said is we're going to describe a measurement of the population. There are 3 different measurements that we're going to have confidence in those. The one we just did is the proportion. The next one is going to be the mean, and then we're going to do the standard deviation. So what I want to do is to talk about how we find the confidence interval for the mean. The confidence interval for the mean has its own formula, which I will put up here for us. And it looks like this. Whoa, try again. Looks like this. Okay. And I will write it down here so I can point stuff to it. Here it is. So when we're looking at this, we are no longer asking people yes or no questions. We are now asking people about a number. So I asked somebody recently, how many shoes do you own? But that's kind of a, I don't know, it's a weird kind of a thing because I think it's going to be very much right skewed. It's not going to be bell-shaped. But if our sample size is large enough, we should be all right with that. So sure, we'll try that. We'll ask people, how many shoes do you own? How many pairs of shoes, right? What single shoes don't really work very well. So how many shoes? And what I'm going to do is I'm going to go out here to Microsoft Excel, and I'm going to put numbers in here to actually make this happen. So we'll do a value of X, and we'll go 30, 20, 10, 5, 8, 9, 4, 7, 20, 30, 10. 10, 20, 30. Right? I think 30 is probably pretty common, but we're just going to say it's not necessarily common. Okay. Now, I have 25 numbers here. These are how many shoes people told me they had. Okay? What do I need from this? If you look at this formula, there are 3 things that come from my sample measurement. What is X bar? What does that stand for? Okay, the mean or the average of the sample, right? What does the letter S stand for?
Is it just sample?
Nope. Standard deviation of the sample, yes. What is N?
Sample size.
Sample size, okay? The number of people that we asked, right? How am I going to find that if I have these numbers? Well, certainly the sample size is relatively easy. Oh, I guess I need one more. I want to make it a little bit easier. Let's put another 10 down here. Because I started with 2, and I go down to 26. So I count this up, I have 25 in my sample. And it's going to be 25. How am I going to find the mean? If I'm using Microsoft Excel. We talked about this, and I think it's in your notes somewhere. But I'm not exactly sure where. It's in your notes. How am I going to find the mean? Looks like Crystal is looking carefully to see if she can find it. Might be in there way back when we talked about finding these things. But in the interest of time, equal sign, average, left parenthesis, select your data. Right parenthesis. Okay. So it looks like this. Average. Bigger. Average, left parenthesis, and then it has the data in it. What's going to happen on your homework is that you're going to be given a set of data. You need to find the average. I do not recommend that you add all those numbers up by hand. I recommend that you put it on Microsoft Excel or something else, and you find the average. So right now I have the average of these 25 as 11.52. That would be the average number of shoes that somebody has. How am I going to find the standard deviation? Equal sign, S is in Sam, T is in Thomas, D is in David, E is in Edward, V as in Victor, STDEV. Select your data again. Right parenthesis. There it is. So it looks like this. STDEV, left parenthesis, and then where your data is located. You could have typed in A2 colon A26 in order to tell the computer where your data is located. Or if you're in the formula and you click onto your data set, it'll do it for you. Either way, you need to do this in order to be able to do your homework. If you do it by hand, it might take you half an hour instead of 30 seconds. I don't want you to take a half an hour, and I want you to get it right more easily by using the technology that's there. You will not have to do this on the test. Most people are pretty scared of saying, hey, you're going to make us do this on the test. The answer is no. But I want you to have the experience of doing this. Okay? So, what do we have for a standard deviation? And just for the sake of doing things, we're going to do this to the hundredths place, 8.32. So this is my mean and standard deviation for this data set. How many shoes do people have? Well, gotta tell you, that was the easy part. Because that's the measurements that we have from our sample. And once we get them in there, we get them. Now we know X bar, we know S, we know N, we can put them in there. What we don't have is T. T is not the same as Z. T is a different thing. So where are we going to find T? Well, we're going to find T in a different piece of paper, which I have to hand out to you today. And that is table F. Table F.
Really?
Thank you. You're welcome.
Can we have some more on Sunday?
Sure, I know you have one.
Only a couple.
Can I take an extra one for Tia?
Sure.
Oh, thank you. Oh, no.
All right, I got them. We got them. So this is not set up the same way as what we had before. This is not set up the same way that table E was set up. What we have here is like that little list of things that I gave you. That's what you're looking at here. These are the actual T-scores that correspond to the different confidence intervals, right? If you look at the very last line, the very bottom of the page, what you will see are the Z-scores. 1.645, 1.96, 2.326, and 2.576. This table actually goes out another decimal place on these. They're still rounded off, but it's giving us the Z-scores that correspond to the different confidence intervals, which are listed at the top of the page. However, what we need to do in order to find the T-scores that I want the T-score of alpha divided by 2. And what I'm going to do is use alpha and what's called degrees of freedom. Degrees of freedom, df is equal to n minus 1. Now the crazy thing about this table is that they didn't have to say degrees of freedom. They could have just put in n and added 1 to it so that it would just have n in it. But they didn't do that because they're crazy. They always think in terms of their formulas. They don't think in terms of, well, who's going to look at this and know what degrees of freedom stands for? It's not listed anywhere on here, but it is. Degrees of freedom is the same thing as n minus 1. So that's what we got to use. So if I'm going to this, and I want to get this right here, go out to my table. Here's table F. Okay. So how does this work? Well, I'm going to want, again, the alpha over 2 is just a label telling me what the number is that I want. If I want a 95% confidence interval, and n is equal to 25, then df is going to be 24. Well, where am I going to look? Confidence interval, 95%, df, 24, 2.064 is my t-score that I need. So once again, what do I need in order to get the right number? I need to know what's my confidence level. 95%, that's going across the top. It does also tell me that alpha, if I have 2 tails, is 0.05, which I do. I have 2 tails. Confidence intervals, remember, always have 2 tails. So I have 0.05 for 2 tails. And then I go down that column until I get to 24, because I have 25 in my sample. Degrees of freedom is 24. So that number is 2.064. What I have right now then are all the numbers that I need to put into this formula to make it work. Well, let's do it then. So I have 11.52 minus 2.064 multiplied by 8.32 over the square root of 25. Then mu, that would be my population mean, which is what I'm actually trying to figure out. And then on the other side, I have the same thing, only with a plus sign. So I'm going to go through the same process that I did with the other one. I'm going to have, bless you, 8.32 divided by, and you got to be kind of careful about how your calculator works, the square root of 25. Okay, I get that number, and then I'm going to multiply it by 2.064. So this number right here is 3.434. So once I get this number, this will be the number I take, and I take 1152 minus that. And then on the other side, I'd have 1152 plus that. Again, it's like my margin of error. And so I'm going to add and subtract those things in there. And hopefully, if I have a mean of 1152, standard deviation of 832, sample size 25, 2.064. There's my margin of error. So for my lower, and like I said all along, the rounding off part, once you get to the end, is not a big deal. During the calculations, you want to try to keep a few digits of accuracy, just to make sure things are going okay. But then at the end, we could say 8.09 and 1495. Well, we will take a break and then we'll come back. We'll do more of this, but I want you to understand what this is talking about right here. Okay. This is not telling me how many shoes people actually have. This is telling me what I think the average is for the entire population. The sample mean was 1152. I know that's not actually correct. So then if I ask the question, what is the population mean? The population mean is what I want, and it's somewhere between these two numbers. So it's telling me what to expect, but only as regards that number. What's the average? It's between these two things. So what if I happened on somebody who did have 30 shoes? From this, I would be able to say, well, that's above average. But what if I had somebody with 14 shoes? I would not be able to say that it's above average. It is higher than my sample, but 14 is in here. So it could be that they're just an average shoe buying person. If it's 14. Even though it's higher than my sample, I don't know that it's higher than the actual population. So this gives me a way to actually describe where the average is, where the higher than average or lower than average, because I don't actually know where the average is exactly, but I know the interval for the average. So that's what we're doing. All right, so we'll take a break. We'll come back. We'll do another one of these, and then we'll move on to the standard deviation. That'll be fun.
Sorry.